If I add all those up, I get an upper Lebesgue sum. And if I go with y sub k minus 1, I get a lower Lebesgue sum. And then I range over all the partitions between of alpha beta, right? And if those two things converge the way, now we know that the lower sums come up, the upper sums come down. If they meet in the middle, that's the Lebesgue integral. So it's the Darboux construction, the Stieltjes construction, but this time we chop up the y-axis. See where that takes us on the x-axis. We have a weight assigned to the pre-image, the little legs that show up on the x-axis. We multiply those by the height we're talking about here. That's a contribution to the area. Add them up over the entire range. That'll eventually be everything, right? It'll eventually be everything. So that's a little big integral. What's the big advantage here? Well, there's a theoretical advantages that will pop up as we do some more work, but one of the big things is this domain here. We picked a very simple case. It's just the real number line. We're finding the area under the curve. This domain here can be enormously varied. As long as it's a measure space, it makes sense. This does not have to be the real number line. This could be a weird space. And the function f could be from the weird space to the real numbers. We partition the reals, those are the y's. They're pretty well behaved. And all we have to do is to be able to find the measures of the pre-images. These pre-images will exist in the weird space. They all have measures. We can certainly form, remember, a measure is a real value function. So the measure of the strange set here times the height, which is a real number, gives a real number squared. That's an area. Add them all up. So what we can do is integrate over very general spaces. So you see this might be an advantage. Previously, we were stuck integrating over lines. The Stieltjes idea was a concession in the direction of general sets. You weight the line a little bit differently. But now you can pick a very strange set. As long as it's a measure space, you can set up some notion of integral, a big integral line. Okay? All right. So, you do the Lebesgue sums. You can read this. What if we combine the Lebesgue idea with the Stieltjes idea? This is possible. We just build the sums differently. Instead of the measure being the ordinary measure of length, we pick a mass function as the function phi. The little notes I've written here. So you use a different measure instead of the length measure, the ordinary length of AB being B minus A. You weight it like you do in the Stieltjes case. Use that as a measure. Form the Lebesgue sums. Let the lower ones come up, the upper ones come down. If they meet in the middle there, that's the Lebesgue Stieltjes integral of a function with respect to that other measure, phi, right, the weighting function. The only condition on phi, other than the sort of the Stieltjes properties there, is that phi behaves like a cumulative probability distribution. The limit of phi is as x goes to minus infinity is 0. The limit as x goes to plus infinity of phi is 1. That's how a cumulative distribution behaves, right? There's no probability to the far left, and there's all the probability to the right. No probability is 0, all the probability is 1. So the phi function here that you use in the Lebesgue Stieltjes formulation has limit 0 on the left and limit 1 on the right, and then you can do it whatever it pleases in the limit. Okay? But it's not negative. As all of those mass functions have to be, they never go negative. Probability, cumulative probability distributions through monotone, increasing non-negative functions with exactly those properties. All right, so that's the little vague Stieltjes situation. This is just a comment about you can define a little vague integral over a weird space. And here's an interesting example of that. It's not in the book. You know what a Banach space is? It's a norm vector space that's complete in the norm. So you have a vector space. Think of R3. Vectors in 3 space. And you have a norm. What's the norm in 3 space? What's the Euclidean norm? The norm of a vector in 3 space is the square root of what? The x component, y component, z component, all squared, added together, and take the square root. That's the length of the vector, right? The vector v, if it's x, y, z, has that as a norm. All right. In analysis, did you study what the Cauchy criterion is for convergence? A sequence is Cauchy if what?
You beginning to, you pass a certain point beginning to elements, and their difference is going to be less than some other time.
No, yeah. Okay, let's try to frame that more actually. It's Cauchy if given epsilon greater than 0, there exists an n such that whenever n and m are mutually greater than n, that implies that the absolute difference between xn and xm is less than 2. Okay, so that's what a Cauchy sequence is. And in analysis, you learn that not all Cauchy sequences converge if you pick the rational numbers. You can have a rational sequence that converges to the square root of 2, but of course the square root of 2 is not rational. So the sequence gets closer and closer and closer to the square root of 2. It wants to converge to the square root of 2, but then the square root of 2 isn't there. Okay, so you say that's a Cauchy sequence, but it does not converge in the space of rationals. The rationals are defective in that regard. They are not complete. They don't have all the Cauchy limits present. A space in which every Cauchy sequence converges is called Cauchy complete. Complete spaces. Did you learn in analysis that a compact set is complete and totally bounded?
Yeah.
Is it coming back to you? Okay. What's compact? Okay. But it's good that you recognize that a complete and totally bounded set is compact. That's good. Okay.
A lot of this that you're talking about tonight, I recognize a lot of them.
Okay. This is, we're doing analysis here. You may need analysis after we're done, but we're doing analysis. Okay. All right. So, a Banach space is a vector space that has this property when these are sequences of vectors. So, we would have a sequence of vectors, and instead of absolute value, we would use norm, okay? So if every Cauchy sequence of vectors converges to a vector in the space, we say the vector space is complete relative to the norm. And a vector space that's norm complete is a Banach space, named after Stefan Banach, a Polish mathematician that died about 1950. He was another genius that sort of burned out a little bit early. His big contribution, or one of many, maybe the biggest, is he recognize the correct generalization, or the most fruitful generalization of these spaces, the vector spaces, real numbers, the direct product of R with itself n times, right? So you have R squared, R cubed, right? The plane, space, 4-dimensional space, 5-dimensional space, umpteen-dimensional space. So you let that go in full generality, and you say the proper generalization is a box space.